In the last lecture, we've already established that kinetic energy is the energy of motion. So if you have a mass, let's use lowercase letter m to represent mass, that is moving, which means it has a certain velocity, then we like to say that this mass has kinetic energy stored in it. If your object is speeding up, it's gaining kinetic energy. And if your object is slowing down, it's losing kinetic energy. And that gain in kinetic energy is not that the energy is being formed out of nowhere, it's that a different form of energy is being converted to kinetic energy. Let's dive a bit deeper into that. So if your object is, let's say, a car, and it's running on fuel, we know that the fuel has chemical energy. If the car speeds up using that chemical energy is converted to kinetic energy. So when I say that the car gains kinetic energy, it just means that the chemical energy in the chemical store of the car is being converted to kinetic energy. And when the car slows down, we know that there is friction between the tires of the car and the road, and there is friction in the engine of the car. So that kinetic energy is lost as either thermal energy or heat energy when the brakes are applied, or as sound energy to the surrounding. So we like to say here that when the object speeds up, it gains kinetic energy, and when the object slows down, it loses kinetic energy. It gains kinetic energy by the transfer of chemical energy to this form, and when kinetic energy is lost, it means that kinetic energy is converted to other forms of energy, let's say thermal or sound energy. So kinetic energy can be calculated using a formula, and that formula is half multiplied by the mass, which is represented by using lowercase m, and velocity squared. Don't forget to square the velocity since that's one of the most common mistakes when doing this question. So here, your mass has an SI unit of kilograms, and velocity has a standard unit of meters per second. So make sure that you do the appropriate unit conversions before plugging in the values into your formula, because you might be given the mass in grams or the velocity in kilometers per hour, and it's necessary that you know how to convert them. One of the easier ways to convert kilometers per hour to meters per second is to simply multiply that number by the fraction 5 by 18. 5 by 18 is the simplified form of 1000 divided by 3600. So let me do that in a bit detail as well. So if you have kilometer per hour and you want to convert that to meters per second, we know that 1 kilometer has 1000 meters. So you're trying to convert 1 kilometer per hour into meters per second. 1 kilometer is 1000 meters, and 1 hour is 60 minutes, and 1 minute is 60 seconds. So that's 1000 divided by 3600, and 5 by 18 is a simplified form of 1000 divided by 3600. Okay, and the standard unit of energy, whether it's kinetic or other forms of energy that we'll be discussing, is joules. Let's do a simple question that involves the use of this formula. Calculate the kinetic energy stored in a vehicle of mass 1200 kilograms moving at a speed of 30 meters per second. So you notice that in the formula above, I used the term velocity and we have speed here. Remember that velocity is simply speed with direction. For example, if you have a car and I say that it's moving at 20 kilometers per hour, then this is the speed because it's the magnitude of how fast the car is moving. But if I tell you that the car is moving at 20 kilometers per hour due east, then we have a direction involved here, and that is the velocity. So speed is simply the magnitude of how fast something is moving, and velocity is magnitude plus the direction of how fast something is moving. And remember that when a quantity has magnitude only, we refer to it as a scalar quantity. And when a quantity has a magnitude and direction involved, that is a vector quantity. Let's come back to our question. First of all, I like to highlight what the question is asking. It's asking you to find out the kinetic energy. Okay? I like to write down the formula of what the question is asking. So kinetic energy equals half mass into velocity squared. Then I like to look at what's given to me and what I have to find out. So I know I have to find out the kinetic energy. Now I'm going to look at what's already available in the question and then plug in the values. So we have the mass given 1200 kilograms. I like to write little letters in my question to make sure that everything's more apparent to me. And if the question has subparts, it's easier to go back to the original information at the start of the question and just grab information from there instead of reading the entire question from the start. So I'm writing a little m on mass, and this is your velocity or speed. Make sure that the units are in their standard form. So we have mass in kilograms and velocity in meters per second. We don't need to do any conversions here. Simply, we will plug in the values. Half mass is 1200, velocity is 30 squared. So 1/2 1200 into 900. Do 1 times, do 6 times 12, 0, 0, 6, 9 times 54, and 4 zeros. And the unit here is joules. And since there is a lot of zeros here, for simplification, we can use the prefix kilo here for these 3 zeros. 540 kilojoules. Next, we have gravitational potential energy. Let's go back to the previous lecture to recall a few concepts. We studied that every mass has a certain region around itself in which it can attract other objects towards itself. Okay? Since Earth has a very large mass, it can physically attract things that fall into its gravitational field. Okay? So when you raise something above the ground, the object that is being raised gains gravitational potential energy, and that is the potential of the object to fall back to the ground. So if you lift an object, the object gains gravitational potential energy, and when you drop the object or when the object falls towards the ground, that gravitational potential energy is converted to some other form of energy, which is kinetic energy in this case. So gravitational potential energy is the energy an object has due to its height in the gravitational field. If an object is lifted up, it gains gravitational potential energy, and when the object falls, it loses gravitational potential energy. And the higher you lift something up above the ground, the more gravitational potential energy it gains. So we can link these things to form a formula for gravitational potential energy. Gravitational potential energy is the product of mass, the gravitational field strength, and the height to which the object is raised. Here, mass is measured in kilograms, gravitational field strength in meters per second squared, and height in meters. And we know that energy has an SI unit of joules. Gravitational field strength has another unit referred to as Newton per kilogram. Let's talk about gravitational field strength for a moment. Gravitational field strength, or little g, it's the strength of the gravitational field, as the name itself suggests. The value of g on Earth is approximately 9.8 newtons per kilogram. And you should remember this value since you'll be required to use it in quite a few places. Whereas the gravitational field strength on the surface of Moon is less than on the Earth by approximately 3 times. So that means that it's easier to lift a mass on Moon than on planet Earth. The gravitational field strength on the surface of the gas giants like Jupiter and Saturn is more than on Earth. That means it's harder to lift a mass on the gas giants than on the Earth. What we're trying to establish here is that the stronger the gravitational field strength, the more strongly is the mass attracted towards that planet, and the harder it is to lift it up. So let's say you have Earth over here, and the Moon over here. If we have the same object on planet Earth and the same object on the Moon, and you're trying to lift these up, you would require a greater force to lift that object from the surface of Earth because the force attracting it towards the planet is stronger. So you would be required to apply a stronger counterforce to lift it up. But if you're trying to lift an object, the same object on the Moon, the force attracting it towards the Moon is smaller, so you would require a smaller counterforce to lift it up. Okay? That's why you must have seen it in videos and movies that astronauts, they are partially flying on Moon. When they jump, the jump is far higher than on Earth because their mass, the astronaut's mass, is attracted less strongly towards the surface of the Moon. The gravitational field strength is how strongly something is attracted towards the center of the planet or mass or Earth, whatever you're referring to. Now, I would like to talk about these two units here as well, even though we'll be covering these in the chapters of motion as well. But I think we should take little concepts alongside to make sure that the repetition is present over there to strengthen our ideas and concepts. So, Newton's second law of motion states that if you apply a force on a mass, that mass accelerates in the direction of the force. If you don't understand this for now, please don't worry, we'll be doing it in much more detail in the section of motion. So this is just for revision purposes. Yeah. So the formula here is F equals mass into acceleration. We have another formula here, which is weight of something is the product of mass and the gravitational field strength. Okay? So your weight is simply the product of your mass and the gravitational field strength of planet Earth. Your mass stays the same no matter where you are, whether you're on the planet Earth or on the moon or anywhere in space, because the amount of particles in your body remain the same. But the value of g changes from place to place. If you're on planet Earth, it's 9.8 meters per second. If you go on Moon, it's almost like 3 times less. So if m is constant but g changes, the product as a whole changes. So the value of weight changes. If g is smaller on Moon, your weight will be lesser on Moon as compared to Earth. Okay? There's that. And then let's talk about units. These two formulas have something in common. M is definitely exactly the same. F, force, is represented as the weight. Remember, weight is a force, okay? And G is in place of A. Now, I can rearrange this formula for G, and I can rearrange this formula for A. This also tells me that gravitational field strength is equivalent to acceleration of free fall, okay? The standard unit for force is newtons, and for mass we have kilograms. For weight, we have newtons, and for mass we have kilograms. Okay? Because force and weight are both the same thing, like weight is a form of force, okay? Now, this is where the newton per kilogram comes from, okay? Now, remember, acceleration has its own unit as well, which is meters per second squared. That is where the two units come from. You have Newton per kilogram by the rearrangement, and acceleration has a unit itself as well, which is meters per second squared. Okay? So G is Newton per kilogram, and G is equal to A as well, which is meters per second squared. So both of these units are correct, but in this context, it's preferred to use newtons per kilograms. I'm sorry if that was confusing. Again, don't worry about it. We'll be doing it in more detail in other sections. This was just a little summary of the concept. All right. Let's do a question for this key idea. A girl of mass 55 kilograms climbs a flight of stairs that's 2 meters higher than the floor. Gravitational field strength is approximately 9.8 newtons per kilogram. Calculate the gain in the girl's gravitational potential energy. I would recommend that you draw a little diagram for stimulating your thought process. So this is the floor, and we know stairs, they go up, and as you go up, you go above the ground. So the flight of stairs take the girl 2 meters higher than the floor. And the mass of the girl is the mass of the girl is 5 kilograms. And the 2 meters is the height by which the girl is raised. And we're required to find out the gain in the girl's gravitational potential energy. So let's write down the formula. Gravitational potential energy is the product of mass, gravitational field strength, and the height by which the object is raised. The mass here is 55 kilograms. We don't need to do any unit conversion since kilograms is already standard unit. The value of G is given to be 9.8. And the value of height is 2. 1078 joules. Next, we have elastic potential energy. We discussed it in the previous lecture as well that elastic potential energy is the energy stored in elastic objects when they're stretched, compressed, or bent. So objects that can change shape by these phenomena of stretching, bending, or compressing store energy in the form of elastic potential energy. And examples of these objects include springs and rubber bands. Let's say you have a rubber band here, and here it's in its original form, it's loose. So when something's loose, it does not have elastic potential energy because it's not stretched, and it doesn't have potential to do anything, right? But when you stretch the spring, and let's say it's like this right now, so you've stretched the spring and you've applied force on these two ends, pushing it out from the two ends, and you've stretched it. Now, in this position, rubber band has the potential to snap back to its original position as soon as you let go of it, provided that it's not reached the limit of proportionality, which is that it's not deformed. So remember that beyond a certain point, your rubber band will be deformed and it won't be able to go back to its original position. But still, it will have the potential to do some amount of work. By work, I just mean the change in its state or the transfer of energy, okay? So what we're trying to establish here is that when the spring is loose, it has no elastic potential energy. But as soon as you stretch it, by applying a force on these two ends, the rubber band has potential to snap back to its original length. And that potential is stored in it as elastic potential energy. So when you stretch something or when you compress something, you're storing elastic potential energy in it. And when you release that, and when you release that rubber band or that spring, that elastic potential energy is lost or it's transferred into some other form of energy. Remember, when the rubber band, a spring, or any elastic object that can change its shape is stretched or compressed, it gains elastic potential energy. And when it's released, it loses its elastic potential energy because that energy is transferred from its elastic potential store to some other form of energy. Now, this is the original form and this is the extended form, and you would see that there is a change in the length of the spring. This change. This change is called the extension. And why did the spring stretch? Because of the force caused by the load. And why is there a force by a load? It's the weight of the load. Remember, weight is a form of a force, okay? So when you hang a mass, the gravity tries to pull it down, and that is the weight. And the force, which is the weight downwards, causes the spring to stretch. And that stretch makes elastic potential energy to be stored in the spring. And if you removed the weight, the spring will go back to its original position, provided that the spring did not deform. You can even do this little experiment by taking the spring out from your ballpoint pen. Okay, it has a little spring in it. You can try to apply force on both the ends by pulling it away from both the ends, and you would see that the spring stretches and it increases in length. But if you apply way too much force, you would see that the spring no longer goes back to its original position because you've deformed the spring. It has passed the limit of proportionality, which means that the force that you're applying is no longer proportional to the extension that you're observing. Okay? So remember that when you're applying a force on the spring by pulling it away at both ends, the spring stretches or it extends in its length. So the force that you're providing is proportional to the extension. But after a certain point, the extension no longer is proportional because the spring has deformed. Now, how to calculate this elastic potential energy? We can calculate the elastic potential energy by using this formula. Half ke squared. This k here is the spring constant. And it's simply how stiff the spring is. The stiffer the spring, or the harder it is to pull the spring apart, the higher the spring constant. It's the flexibility of the spring. So remember, you might have seen springs that are very easy to stretch and springs that require you to apply a far greater force to stretch them. So, how flexible or how easy it is to stretch a spring is determined by the spring constant of the spring, okay? And it's a property of a spring that's constant and unique for every spring. The units for spring constant are newtons per meter. These units come from the formula of Hooke's law. Let's do a review of Hooke's law. Remember, I'll be covering these concepts in detail in other lectures, but I like to give a little summary wherever something comes up to make sure that we keep on revising things while learning new things. So Hooke's law is simply the force a spring experiences is equal to the product of the spring constant, which is the stiffness of the spring, multiplied by the extension. Okay, so the greater force you apply, the more extension you observe. And we know that the units of force are newtons and the units of extension are meters because it's simply a length, right? So if you rearrange, you would see that the units of K or spring constant are newtons per meter. Here. So here's your spring constant in newtons per meter. Your extension is simply a length. See over here, your extension is simply an increase in length, right? So length has a standard unit of meters, and when it's squared, that means extension squared has a unit of meters squared. And I think we should just leave it to meters because it's extension that's squared, so you know that extension is simply meters and you can square it in your units as well. Energy, like always, is joules. Let's do a question now. A mass is attached to the bottom of a hanging spring with a spring constant of 250 newtons per meter. It stretches from 8 centimeters to 9.4 centimeters. Calculate the gain in elastic potential energy. First of all, highlight what the question is asking you and write down the formula of that term. So elastic potential energy is half K E squared. E is simply your extension. You are required to find the elastic potential energy. Your spring constant is over here. Okay, and your extension now. So it stretches from 8 centimeters to 9.4 centimeters. Let's draw a little diagram to understand the question first. So you have a spring that's attached over here, and its original length is 8 centimeters, okay? So its original length is 8 centimeters, and it stretches from 8 to 9.4 centimeters. So after you hung a mass on it, it stretched to 9.4 centimeters. So its new length here is 9.4 centimeters. So this is the original and this is the new length. What's the change in length? This here is your extension or your x. So x is 9.4 minus 8 centimeters. Half k is 250 newtons per meters, and x is 9.4 minus 8 centimeters. Okay? Half into 250 into, now 9.4 minus 8 is 1.4, but it's centimeters. We want meters, remember, okay? The unit here should be meters. So I'm going to convert centimeters into meters. You should remember this conversion factor here. Meters to centimeters and centimeters back to meters. 1 meter has 100 centimeters, so you can multiply with 100 to get that. But if you're converting from centimeters to meters, you divide by 100. One way to remember when to multiply and when to divide is to think of how big or small something is. A meter is larger than centimeters, right? So if you're dividing a meter into centimeters, you're multiplying it because it has a lot of centimeters into it. But a centimeter doesn't have a lot of meters in it, right? Because a centimeter is smaller than a meter. So you would divide by 100 to get to a meter, okay? So to convert centimeters to meters, I will divide by 100. 1.4 divided by 100 is 0.014 meters. So I'll plug in 0.014 meters here. Remember to look out for the units. If the question gives you units of centimeters for length, you must convert this into meters for the calculation to be correct, okay? Now that we've studied kinetic energy, gravitational potential energy, and elastic potential energy, it's time to link these three and see the relationship between them. So we will be studying the relationship by looking at a mass hanging on a vertical spring that oscillates up and down, and when the spring oscillates up and down, there is a change in its position, right? So if this was the equilibrium position or the rest position of the spring before the mass was displaced to cause the oscillation, um, this is the spring oscillating up and this is the spring oscillating down, okay? And the center one, this is the rest position of the spring, okay? So when the spring is at rest position and you provide a little push to the mass and it oscillates up and down, let's look at position A, B, and C. At position A, the spring is compressed, okay? And since the spring is compressed, it stores elastic potential energy. And since the spring is compressed to its fullest at its far above position, it won't move, it will temporarily stop. And when there is no motion momentarily, then we can also say that the kinetic energy is zero at that point. And at point at point A, since the spring is at the highest position from the ground, the spring has the most amount of gravitational potential energy stored in it. Remember, the greater the height, the more the gravitational potential energy stored, okay? So the gravitational potential energy here is maximum. Let's look at position B. In this position, the spring has some form of elastic potential energy since it's slightly stretched, right? It's stretched. The spring is still moving because, here, let's say this is the rest position, it goes up and then comes back to the original position and then goes down. And it's still in motion when it's at its rest position. I wouldn't call it a rest position, let's call this the equilibrium position, okay? So this was the spring, this is the mass here, and this is the spring, okay? And you displace it, it goes it goes up, and then it comes down and goes down past its equilibrium position. So at its equilibrium position, it's in motion, okay? So at position B, the spring is in motion. Let's talk about all three forms of energy. It does have some form of elastic potential energy present. It does have some form of kinetic energy, and it definitely has some form of gravitational potential energy because it's still above the ground. But the gravitational potential energy here is less than here. But the kinetic energy here is maximum. Because over here, it's going down, right? And it's at the highest velocity when it's in the middle position, okay? At position C, the spring is stretched to its maximum. So the elastic potential energy is maximum. The kinetic energy here is zero again because when the spring is at its lowest, it momentarily stops before it can go up. So when it momentarily stops, its velocity is zero. So the kinetic energy is zero, and the gravitational potential energy is minimum because it's closest to the ground. Okay? The less the height, the less the gravitational potential energy. Let's revise this concept. What we're observing here is a spring which has a mass hanging at the bottom, and the spring oscillates up and down. Try to visualize this, okay? When the spring, okay, so this is the spring and you have a mass, okay? This is the rest position. By rest position, I mean the equilibrium position, okay? It doesn't mean that it's at rest over here, it just means it's at equilibrium position. And you provide a little force and you displace it, and then you would see that the spring oscillates up and down from the equilibrium position. When it moves up, it's compressed and it gains elastic potential energy and it gains gravitational potential energy because it moves above the ground. And at its topmost position, it momentarily stops before it can come down, right? And when it momentarily stops, it has zero kinetic energy because when the velocity is zero, the kinetic energy is also zero. Then when it's at its topmost position, it momentarily stops and then comes back down. When it's coming back down at the equilibrium position, now it has the highest velocity or the highest speed. So the kinetic energy at the equilibrium position is maximum. At the lowermost position, its gravitational potential energy is minimum because it's closest to the ground, and its elastic potential energy is maximum because it's stretched to its fullest. Okay, so at A, gravitational potential energy is maximum, at B, kinetic energy is maximum, and at C, elastic potential energy is maximum. A student goes for bungee jumping. The cord has an unstretched length of 20 meters. The diagram here shows you the before and after situation. The mass of the student is 60 kilograms, and the value of G, or the gravitational field strength here, is 9.8 newtons per kilogram. Part A change in gravitational potential energy at 20 meters. So I'd like you to pause the video and maybe give it a try and then look at the solution to check whether you got it right or not. So gravitational potential energy is simply mgh. Let's plug in the values. Mass is 60 kilograms, g is 9.8, and the height is 20 meters. Plug those values in your calculator and you would get 11760. Don't forget the unit. Alright, the next part asks you to find out the maximum change in the gravitational potential energy. Gravitational potential energy max. Now, maximum gravitational potential energy is when the height is maximum. And you see height of 70 meters when the bungee cord is extended to the maximum position is when the height is maximum. So you will use the same formula, mgh, and plug in values into this formula. The mass and the value of g is the same, and the height this time is 70 meters. And we have 41160 joules. C part asks you to find the speed of the student after falling 30 meters if 90% of the gravitational potential energy is transformed to the student's kinetic energy. So let's see what we have for now. We have the gravitational potential energy at 20 meters. So gravitational potential energy at 20 meters is equal to 11760 joules. 90% of this gravitational potential energy is converted to kinetic energy. So kinetic energy equals 90% of the gravitational potential energy at 20 meters. So what we're trying to do here is to find out the kinetic energy equals 90% of this value, 11760. So the kinetic energy is 90 over 100. We can write a multiplication sign in place of 11760, and that equals to 10584 joules. Now we have to find the speed at this point, okay? So we know that kinetic energy has the formula half mv squared. We know the mass of a student was 60 kilograms, and velocity is what we're trying to find out squared. Now, before we do this calculation or plug in values, I'd like to take a step back and isolate v, okay? Because it gets a little complicated when you have plugged in the values and then you try to rearrange it. I prefer rearranging it first and then plugging in the values. You want v, right? So you're going to isolate v. First of all, let's take this half on the other side. Or we can say that this 2 is being divided by 1 here, so when it goes to the other side of the equal sign, the operation is reversed. So if it's being divided here, it will be multiplied on that side. So 2 multiplied by kinetic energy. Equals mv squared. Now, if this mass is being multiplied with v squared on this side, when you take it on to the opposite side of the equal sign, it will be divided. So you have 2 kinetic energy divided by mass equals v squared. Now you have a v squared, so you've isolated the v, but you don't want the square of it. So to undo the square, we take an under root. To cancel the square, I'll take an under root here, But if I do one operation on one side of the equal sign, I have to do the same thing on the other side of the equal sign. So I take an under root here as well. Now, this square will be cancelled with the under root, so you have v equals this entire thing here. Now we've established a formula to find out v. All we need to do now is to plug in the values. So v equals under root 2 into, what's the value of the kinetic energy? Over here. What's the value of the mass? 60 kilograms. Plug these values in your calculator and you would find your answer to be 352.8 square root, and that's equal to 18.783 meters per second. First of all, we know that the gravitational potential energy is converted to the elastic potential energy. So the gravitational potential energy that we calculated was 41160. So that gravitational potential energy has been converted to elastic potential energy. So we can say that elastic potential energy is equal to the gravitational potential energy, which is the value of 41160. And now we want to find out the spring constant. So we'll be using the formula of elastic potential energy here. Elastic potential energy equals half into spring constant into the extension squared, okay? We want K, so I'll rearrange the formula for K, and I'll get 2 multiplied by elastic potential energy divided by extension squared. How did that happen? This 2 is being divided here, it goes to the other side, and it's multiplied. This x squared is being multiplied here, it goes to the other side of the equal sign, and it's divided by the terms. Now let's plug in the appropriate values. 2 into elastic potential energy here is 41160, and your extension squared. Now remember, the unstretched length was 20 meters, and when it was stretched, the length was 70 meters. So the extension is 70 minus 20, which is 50 meters. So you have 50 squared. And the value is 32.928 newtons per meter. Lastly, we have thermal energy. Thermal energy, in simple terms, can be referred to as the amount of heat retained in an object. And thermal energy is responsible for the temperature of an object. The hotter the object, the more thermal energy it has, and the higher its temperature, okay? The amount of energy needed to raise the temperature of a given mass of a substance by a given amount can be calculated using this equation. E equals mass into C into delta theta. Now this m is the mass of the object, and it's measured in kilograms. C is the specific heat capacity. Specific heat capacity. Its unit is joules per kilogram degrees Celsius. And delta theta is simply the change in temperature. Theta is temperature, and delta is representing change in degrees Celsius. Now, what is a specific heat capacity? This is a property of matter, okay? It's the amount of energy that's required to raise the temperature of 1 kilogram of substance by 1 degrees Celsius. So let's say that you have a kilogram of a substance, okay? How much energy would you need to raise its temperature by 1 degree Celsius? Let's say that its current temperature is 20 degrees Celsius and you want to raise the temperature to 21 degrees Celsius. The amount of energy that you consumed to raise that temperature of 1 degree Celsius is the specific heat capacity of that material. And matter of different types has specific heat capacity of different values. For example, a copper block has a specific heat capacity of 390 joules per kilogram degree Celsius, and water has a much higher specific heat capacity of 4,200 joules per kilograms degrees Celsius. So, specific heat capacity, we use the letter lowercase c to denote specific heat capacity, is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Different substances have different specific heat capacities. For example, we have copper, silver, and water here. Copper has a specific heat capacity of 390 joules per kilogram degree Celsius, silver of 910, and water of 4200. As you see, the specific heat capacity increases from copper to water. Now, let's look at the properties of these three types of substances. We see that copper heats up faster than water and it loses its heat faster than water as well. Like if you were to take a metal spoon and put it on heat, and on the other hand, if you were to take a container of water and put it on heat, you would see that the metal spoon heats up faster than water because the specific heat capacity of that metal spoon or copper is less than water. So, substances that have a lower specific heat capacity heat up and cool down faster. That means that they take less energy to change their temperature, whereas substances with higher specific heat capacity heat up and cool down slower. Okay, that means that they need higher or more amount of energy to change their temperature. So, specific capacity is mainly used for liquids and solids, okay? And the specific heat capacity of different substances helps us determine how useful they would be for a specific purpose. For example, for choosing the best material for kitchen appliances. Good electrical conductors like copper and lead are excellent thermal conductors due to their low specific heat capacity. Since they heat up pretty fast, we would want to use them in conducting purposes like for making heating pans, etc. On the other hand, substances with lower heat capacity like water um, makes them ideal for heating homes as the water remains hot in the radiator for a long time. Also, this equation is pretty important. MC delta theta. You should know how to rearrange the equation to find any of the unknown values. Energy in joules, mass in kilograms, specific heat capacity in joules per kilogram degree Celsius, and remember to find the change in temperature. Don't just plug in the temperature, you're required to find the change in temperature. Let's do an example question to understand how you might be required to use this formula. You don't have to necessarily memorize it because this equation will be given on your equation sheet, but you should know how to use the formula. So let's say that a substance of mass 4,000 grams has a specific heat capacity of 201 joules per kilogram degrees Celsius, and its temperature is raised from 20 kilograms 20 degrees Celsius to 58 degrees Celsius. How much energy is required to do that? Simply write down your formula, MC C, delta, theta. Plug in values. Mass is given in grams, so you have to convert it into kilograms. 4 kilograms, the value of C is 201, and the change in temperature from 20 to 58. So what's the change? It's 58 minus 20, that would be 38. Plug in these values in your calculator, and you would get your answer to be 30,552 joules. And you can also write it to be approximately 31 kilojoules. Okay, now this concept can be a bit tricky to memorize, so let's use an analogy for this. Imagine a dry sponge which you put under a tap, okay? So the sponge will absorb the water until it reaches a point where it can no longer hold any more water and it will start to leak out of the sponge, okay? So you have one example of a sponge, okay? And on the other side, you have a brick. Now, if you did exactly the same thing with the brick, you would see that it would not absorb much water and it would start leaking way ahead of time, like way earlier. The sponge has a greater water capacity than a brick, right? It absorbs much more water before it leaks out. In a similar way, substances also have a different capacity for absorbing thermal energy. Those with a greater heat capacity can take on more thermal energy before their temperature rises than other substances.